Hey everybody! Today I'm going to explain to you the principles of fluid dynamics. On one of my previous videos, I made basic aerodynamics, so how a wing enables an airplane to fly, difference of pressures. Feel free to go watch that video, and if you don't want to, if you already know it, then it's going to be helpful. You will understand this a bit easier, hopefully. So first of all, we're going to talk about internal stickiness, which is viscosity. Now, viscosity of a material is how fast a fluid flows, okay? Because of shear stress. Now, shear stress is when you have two forces, one going this way, one going this way. That's what we call shear stress, okay? Now, we're going to use viscosity to understand how a fluid flows, okay? So first of all, we're going to talk about the what happens if you have two plates, okay? Now here we have four different scenarios of a liquid, or no, sorry, a fluid, okay? Fluid is just a liquid or gas. Liquid is just liquid. My bad. Anyways, so you get two plates, and then on the first scenario, you have a fluid that is in vertical position, okay, with no velocity. So there is no speed, and the change in direction of vertical direction that is going to be used later for some calculations, okay. And here we haven't even started, so this is before the time even starts. Now we are going to move the lower plate to this direction, okay, to the right, okay. And so when we start doing that, then you get an L shape. The fluid flows in an L shape, okay, just the moment it starts. Then after that, you see it to be in a curve, and then the more time you take, then what they call it becomes like a linear line. You know what I mean? Okay. So now we're going to talk about how to find that shearing force and that shearing stress using something called Newton's law of viscosity. Newton has made so many laws, right? Okay, so this one we got force. Now mu is viscosity, okay, and A is the area. Obviously, most of the times A is area, but you never know, okay? They always change letters. Anyways, and then you do viscosity times the area, multiply by the change in velocity over change in y. So that is going to be maybe a derivative as well, you know, when you have change in something over change in something else. So that is the gradient, okay, how like the change in velocity over the change in the direction of y in the plate. And then tau, so that little t that looks like a t, that is not a t, actually that is just a Greek letter, another Greek letter that you have to learn. There you go. It's tau, we call it tau. And then so stress is force over area, right? We should be knowing that, hopefully. And then obviously you just rearrange the equation, you get mu times change in velocity over change in y. Now here we could also instead of putting the delta, that triangle's delta, we put d, and then you could see it's in terms of a derivative, okay? So it's like a differential equation at that point. And then on the right you got a graph of change in velocity over change in y, and then with tau, and you get linear. So that means viscosity is linear. So it's not the case for every fluid though, like it's just with assumptions. We love assumptions. It makes everything simpler. So now we have two things, kinematic viscosity and Newtonian viscosity, and this is again where I said assumptions and how different fluids could be different so we can make our life easier. Now kinematic viscosity is used where we assume saying viscosity and density is the same thing, single property. This is to make our calculations easier, so life easier for some parameters, okay, so not everything. Now that little v, okay, is our kinematic viscosity, and we can calculate it by mu over rho. So both of mu and rho have the same units, which means kinematic viscosity is going to be constant. Wait, am I right? I'm actually not sure, but yeah, I think yeah, whatever. Anyways, Newtonian fluids. Now this one, it is like fluids with constant viscosity. So you know on the previous slide where we talked about Newtonian fluids and the concept of fluids with shear stress. So here where you had that linear graph, okay, so we always say that shear stress versus the shear rate relationship is linear, okay, no matter what shear is applied. Now this only applies on some of the fluids, definitely water, okay, most gases and molten glass, okay, so there you go. Now, so what about if a fluid is not Newtonian? So we got here three different things, Bingham pastes. I don't know how to say, okay? So that is like toothpaste, okay? So this is what happens, okay? So shear stress, right? So that tau O, initial tau, it must be like it can't be like 0 or like 1 for it to start to flow. There is a like a minimum, like a threshold, where if it exceeds this like stress, then it will start flowing, okay? So for example, toothpaste, you know, you're going to put some toothpaste on your brush. You have to squeeze it and it doesn't quickly just go down, right? Or printing ink, okay? So then shear thinning. So it becomes less viscous as shear stress is applied like paint. Just think about it that way. And then shear thickening, that's the opposite, which is like cornstarch plus something, you know? Now, so we have 6 ways to classify fluid flow, okay? So we either have steady flow, viscous flow, and laminar. So, or we can have unsteady, inviscid. I'm really bad at saying words, okay? And then turbulent, okay? So these are just the opposites of the other 3 ones I said. So now we're going to explore them more in detail. So, viscous versus inviscid flow. Now, viscous flow is where you have like the viscous effect is important and you can never ignore it. So, how the fluid flows, you cannot ignore it as an assumption for some of these fluids. Now, inviscid is one where like the viscous literally effect is not that significant on the flow and sometimes can be negligible, okay? To model it, we set like a viscosity to 0, okay? So then we don't have to worry about viscosity. So that is for stuff that like barely flow, I think. So experimentally, like it's difficult since all real fluids like water and air have some viscosity, okay? Now we have something called the boundary layer. So the boundary layer is something like, let's say you have an object, like a solid object, okay? Now, just leave it on a table and you got air. Air is a fluid, it's got some viscosity, okay? Obviously, every fluid has viscosity, okay? And then you put that air, so it's all around it. Now that there is something called that boundary layer, okay? There is a layer of air, like the closest one, near the solid. What happens is that because of its shear stresses of and viscosity of this air, it creates a bit of friction. Outside this, it's like a thin boundary layer, okay? Outside that layer, then you got like, it don't interfere, okay? So then the effects don't exist anymore outside that layer, okay? Now, laminar flow versus turbulent flow. So, laminar flow, as you can see here, okay, you got like some sort of tube or something, and then you got the flow of the fluid particles is going from the left to the right with the arrows. So it's laminar because it flows nicely, easily. It's not mixing with any other part, like fluid particles. It's just smooth and parallel, okay? So everything's organized. Now think of turbulent flows like that. Everything is everywhere else and it's just, okay? So it's very irregular and chaotic, okay? So this is because where velocity and pressure can vary a lot with space and time, okay? And that is because the fluid particles is colliding or mixing with the other neighboring fluid particles. So all of that like weird stuff is happening. Okay, now if we're talking about laminar flow, we need to talk about Reynolds number. Reynolds number is like a dimensionless constant, okay? So you've got different like values. It's like every fluid will have its own Reynolds number, and it's like that determining at which point where a fluid becomes laminar or turbulent, okay? So we use dimensional analysis to find that number. We have density times velocity times diameter of the pipe or whatever object you have, all that divided by uh, viscosity, okay? So if you have a small Reynolds number, okay, the flow is going to be laminar, okay? But if you have a very large Reynolds number, the flow is going to be turbulent. So we have the critical Reynolds number, where we know where the transition is from laminar to turbulent. If the Reynolds number of a fluid, okay, is smaller than the critical Reynolds number, then the flow is laminar. However, if it's larger, then the flow is turbulent. Now, it all depends on geometry to find the Reynolds number, the critical one. So if you have parallel plates, you get 1500 flow inside a rough. Well, so you got all this table, you can know what it is in every, so it changes in every geometry, every environment you have. Now, we are on the third flow description, the steady state and dimensionality, okay? Steady state flow. So the steady state flow is a condition of a flow, okay, where like the flow properties do not change with time. So at that time, it don't change anymore, okay? We have this equation here. We got change in phi. Is it phi? Too many Greek letters anyways. So that Greek letter is any flow variable you have, like viscosity, density, velocity, over the change in time is going to be 0, okay? So because the flow is 0 with respect to time, then it is steady. Obviously, it's very obvious, I think, right? Now, in general, okay, fluids are 4-dimensional. So how does that work? So the 3 dimensions is the XYZ in 3D models. The fourth one is time, okay? So time is a dimension, okay? Now, when it's a steady state flow, time does not exist, okay? Now, what if it's 1D? If it's 1D and the flow actually changes with time, then you got 2. So here's like some functions you could use. Don't worry about it much. We're not going to dive into it a lot. Maybe in some other videos, hopefully. So now this one, incompressible, uniform, and streamlined flow. So first of all, incompressible flow is where the density is constant, no matter the flow field, okay, where anywhere in the flow field. Now Mach number, okay, is the speed of the fluid, okay, over the speed of sound in that medium, okay. Then isothermal, so this you hear it a lot. Iso means the same, thermal means temperature. So here temperature is constant everywhere in the flow field, okay. Then you've got inviscid flow, which we already talked about in the previous slides. Then now we got streamline and stream tube, okay. Now streamline, okay, is like line, okay, so where when the fluid is flowing, then slowly it all just goes into one direction, okay, horizontal direction. Do not think about this much, it's not that important for now. Now, continuity equation, okay, this is cool, and after this we're gonna talk about Bernoulli's. You've heard a lot about Bernoulli's, I bet. Now, first of all, we need to know what a control volume is. So we might have fluids flowing through something, right? We have to make a control volume, so where we can, obviously it's going to be very difficult to calculate for whatever you want when it is everything is around it, the whole world. So you will have so many stuff affecting it, but if you put it into a control volume, then you're just simplifying it, okay? So first of all, now we're going to simplify this, get into the easiest part, where we've got this equation, okay? Rho 1 C1 dA1 equals rho 2 C2 dA2, okay? And which equals a constant. So what does that mean? Okay, what does that mean? Right, this is gonna be a long video. Anyways, here it's just the conservation of energy. Remember the law of conservation. Energy cannot be made or destroyed, okay? Same thing with mass. It can't just, if a fluid is going through a control volume, when it enters and when it gets out, the mass should be the same, okay? Unless it's stuck somewhere in the control volume, the energy must be the same, okay? So to make sure of all that, we have this equation. We can use it, this formula, to find the missing, if like we know some of the variables that is going into the control volume, and we need to find the other quantities of these variables when it's getting out of the control volume. We use this equation you've seen here. So rho is density. So when you see 1 subscript 1, that means that's initial when it's getting into the control volume. And dA is just change in area, okay? So now what about mass flow rate? So mass flow rate, m dot, means the change in mass with respect to time, okay? Now we say that m dot, okay, equals rho times time times area, okay? A is the cross-sectional area of the flow passage, and yeah. So this on the left is just the derivation, and I think no one loves derivations. You're never gonna use it if you're an engineer. All you need to know is the short part, okay? It's gonna be a very long video, I'm really sorry. Yeah. Now, so this is just, we use the continuity equation differently, depends on the flow. If you have incompressible flow, okay, you're gonna use this equation, as you see here. Now, so this is more a bit about like thermodynamics. Okay, so here is the derivation from energy conservation. Okay, this we will be talking about it more in detail. This is Bernoulli's. We have four assumptions. First of all, it's an ideal fluid, so no shear, no change in internal energy. It is ideal. Okay, steady state flow. It won't change with respect to time. Incompressible flow, and it's 1D uniform flow. That's a lot of assumptions. That is not real at all, but we want to make things simplified and yeah. And then again, just like the continuity, we are using the conservation law, but this time with energy instead with mass. So here we know. So first of all, we got three energies, okay, in this control volume with the fluid. You got the potential energy, which is mgh, kinetic energy, half rho c squared, right? So now here we don't use m, and that is for a reason, because the mass is not okay, not taking into account. Anyways, we got static pressure energy, that is just pressure times v, velocity. Okay, so now what we all we have to do is say that, okay, when you add these energies before it enters the control volume, it should be the same total energy when it exits it, but probably like some of the energy from the potential could change into kinetic, vice versa. But we know that the total must be the same from in and out. Now, okay, how do we derive this, right? Again, I hate derivations. I really hate them. Now, that's just Bernoulli's equation again, but we use something different. We use F equals ma, so that's Newton's second law. In a nutshell, you end up with the equation or the formula down there where you got pressure divided by density plus c squared over 2 plus g z. Now g is gravity, z is a dimension. It should be in constant, so when it enters the flow control volume, that total should be the same when it exits it. Okay, now we got three different forms, and they're all the same, by the way, but it's just different variables depending on what variables you have. Okay, so we got the energy form, which is the one we just looked at. We got the pressure form, and then we got the head form. You could just see the first one is pressure energy plus kinetic plus potential. Second one, static plus dynamic plus potential energy, pressure. The third one, static plus dynamic plus elevation. It really depends on the flow, where it's flowing, the control volume. You will always know which one to use, okay? So do not worry about it. Right. Now we got different things. We got the YouTube. I don't mean YouTube. So YouTube. Okay. You get me. You're reading it. A manometer. Okay. So that is like a U-shaped manometer. Okay. It's like a. So what everything we need to know about this YouTube thingy. It's like it measures pressure, right? You could measure the pressure of a gas using the height difference. Okay. The height difference of that U-tube. Okay, so if you're putting a fluid in it and then you want to find the pressure in that fluid, it's the change of height. So it's cancelled out by raising a column of liquid against the gravity. Okay, now I don't have a YouTube manometer with me to show you, but yeah, it's just that's the formula. All you have to know is that change in pressure is just obviously P1 minus P2. changing, okay? And you could know that P equals rho GH. So if you know G and you know, obviously, you know change in H, you get the change in density, and then you get the change in pressure, okay? Now, stagnation point. Oh my god, yes. Okay, this is finally something I love. So basically, all you have to know is that it's the point in the flow field where the fluid particle is brought to rest. So think about it. You've got a solid, okay? And then you got some air flowing towards the solid. Now, when the air that hits the solid, it's going to stop. And it's going to be separated and go around the solid, okay? So this means total pressure is going to increase, okay? And dynamic pressure decreases. But yeah, anyways. So now we have to talk about Pitot tubes. That's another thing that I hate, just like the YouTube Orifice plates. Yeah, they have their own formulas. They were derived again. I don't love derivations. I think I've said I don't know how many times I said that in this video actually. So pitot tubes are actually used in airplanes or aircrafts to calculate the actual airspeed. Okay. Now, how does that do it? Does it do it? We have to first assume again that static pressure is constant. We use the U-tube manometer to find the difference in pressure, okay? And then, so it depends what you have to. Anyways, you find C, which is the velocity, okay, of the airspeed, okay? Anyways, you just use that formula, root square of 2 times change in pressure over change in rho. You get the change in pressure from the U-tube. You get a pitot-static tube, okay? Now, actually, we talked about aircrafts using pitot tube, but pitot-static tube is actually used more often because it's more accurate, okay? Because remember, in the pitot tube, we're assuming static pressure is 0. Not 0, sorry, it's constant, okay, constant. And if we want to find the airspeed, we use a pitot-static tube. So what it does, it gets your stagnation pressure, which is from the U-tube manometer. There's different ways you can do it actually, not just the U-tube manometer. And then you get your static pressure as well using that tube, and then you minus them, and then you get your total pressure. It's used in airplanes for the pilot to know. It's usually mounted on the wings, if you know what I understand, what I mean. So now Venturi meter, and then after this is Orifice. I just know it, okay? Now Venturi is made up of 3 sections, okay? It's kind of like a nozzle, like reminds me of engines for some reason, which is kind of similar. Anyways. So what it is you get a convergent section. As you see on the left, you get like a tube, or not a tube, like a meter. It converges. You get the throat, and then it gets bigger. Okay. Now, so first of all, okay, it is used to measure the flow rates of a fluid by doing something intentionally converging, okay, getting to the converging section, making it smaller into the throat, and then the diffuser making it bigger, making a control volume so that you get the difference of pressure, like the pressure drop. Now we have to apply Bernoulli's again here, okay? When we apply Bernoulli's here, we get this formula. You get V equals A1, which is a cross-sectional area, okay? That A1, that's the initial. So on the convergent side, before you get into the convergence, okay? So anyways, that is just between the entry and throat, okay? Now, so no, like this equation is used for that. And then you get multiplied by square root of 2 times, you've seen that equation somewhere, right? You've seen it in the opposite. Just note this down and you can use it for questions, okay? Orifice plates. Okay, this is the last slide. Finally, it's been 30 minutes. I just knew it. We'll be doing orifice plates. Now, this is similar to the previous one, the Venturi, except, so it's like a metal, okay? Metal, circular metal thingy with a hole inside. You place it in a tube. The tube is constant like that, okay? But when you place it in a tube, it makes the fluid have to go through that little hole and get out. So it makes a similar effect as the Venturi, okay? Yeah, it's to find the pressure drop and then the flow rate of a fluid. So then you use that equation, okay, that formula. Now, because of friction, again, we hate friction. It always ruins everything. Friction means that actually the real flow that we calculate is always going to be lower than the one we calculate. Okay, okay. The real flow is lower than the ideal calculated one. So to do that, we have something called the discharge coefficient. We have one for Venturi meter. We have one for Orifice meter. All you have to do is multiply the one you've got with the ideal flow you got, and then you get the actual. Yeah. So that's it. It's been a very long video. I'm really sorry. It's kind of like a lecture at this point. But I really hope that this helped you. Yeah, it's actually a very tough topic. But once you understand it, it becomes really cool, actually. Yeah, and then you get more into aerodynamics. It actually gets a bit worse, but then you get used to the difficulty. Yeah, I'm gonna stop yapping. The video is already too long, but I really hope you enjoyed it and have a lovely day.